So today we're looking at how you do 3D volumetric scalar field display. We're kind of in the grind now, right? So it's like the good news is there's no final project, there's no tests, and there's no midterms. If you all brought your ones that you wrote in, please bring them up here and set them up at the front. I just want to kind of look through and see if people are on the same page. No graded ones. But the bad news is the homework is going to grind for the next like 4 weeks, right? So we're going to be in this mode where we're seeing a lecture on one particular technique and then doing a homework by the next Thursday on that technique while reviewing the last people's homework from the previous week. And so it kind of ramps up and gets busy through this time. We're going to start here with a couple of examples. Thank you. Excellent.
Tangential confocal microscopy data.
So it's 3D data from microscopy.
Basic operations.
Whoa.
In this video, we show the basic operations of our confocal visualization tool. First, we open 3 volume channels from a confocal data set and wait for the channels to be loaded. The loaded volume data is now listed in the data view. Next, we add all 3 channels to render view 1. Their colors are assigned automatically according to the order in which they are added. Next, we
So
rotate.
which of those colors was automatically assigned that was not a good color?
Blue.
Yeah, why is that?
Is it black background?
Black background is no luminous contrast with the black background, right?
Rotate the view to check the rendering quality. The default rendering mode is layered mode, but we can quickly switch the rendering mode to depth or composite.
We're going to talk about that today, what those
Next,
different
we
modes
set
are.
each volume's transfer function settings. We can adjust boundary extraction, low and high thresholds, gamma, and offset.
Are we looking down at a brain or on at someone's face?
This is a fly head.
So no was the answer. Fly head. Okay.
2 big eyes and a brain.
They made a movie about that then.
The fly.
These adjustments produce a better visualization of the volume data set. When everything is done, we can save the project, including all parameter settings.
Yeah, yeah. All right.
BO, we show how we use depth cueing and shading effects to visualize the overall and local features of a volume data set. The loaded channel shows all the cell nuclei in the zebrafish head. We can rotate the view to see how applying depth cueing helps to reveal the shapes of structures, like the eye and brain regions. We can adjust the degree of depth cueing to optimize the visualization. Next, we can see how shading effects can enhance the visualization of small surface structures. Embedding polygon data. In this video, we show how to use polygon data for defining subregions and displaying them in different colors. This data set shows retinal ganglion cells which connect from the eye to the brain. We then load the polygon data that represents the eye region into the view.
All right, so this was some magical segmentation they've done outside the visualization program to select a region.
We use the trim command to separate the volume data into interior and exterior subvolumes using the polygon data in the same view. Next, we can independently set volume properties, such as display color, for the interior and exterior volumes.
Are you kidding me? Green and yellow?
Yeah. So at least they both include a lot of luminous channel, but they're very saturated. So in VolView, or sorry, in ParaView, if you want to do something like this, you can use a clipping plane to kind of clip part of the data and then set one set of transfer functions in one part and another part in another. The way you do the other part and the other is you have two clipping functions. You load the data set twice, you clip once to get this part, you clip another time to get the other part, and you do that. You can also do region of interest to pull out a particular location. All right, this is an approach that we're not going to see today otherwise. The idea here is not to extract an isosurface of the same density of this particular data set, but rather to do a computation that looks for local maxima, right? And so this is looking at a turbulent jet or a fire simulation with a bunch of turbulence, and they want to understand what these structures are. So rather than trying to find an isosurface value that will capture the feature of interest, they find any location where there's a local maximum. It's kind of like, you know, burning to the local minimum and showing the medial sections of these high kind of temperature regions. That's something I don't know how to do in ParaView, but hopefully someday we'll have that capability. So when you're doing your final project design, you're going to do two things. One is an ideal design, and one is the one we could actually do. And so be keeping of all these methods, even the ones that you can't yet do in ParaView or your visualization tool, and say if we could do the ideal design, this is the one that we would pick. Because as you go into the future, we're going to have more and more things implemented in the toolkits, and you'll suddenly be able to do that. All right. Okay, so before I go into the volume display techniques, I'm emailing you out whenever I get ideas from people in the class or answer somebody's question in the class, tips for using ParaView, how to do different things in ParaView. If you come up with a technique that works, it's fine for you to go ahead and post that to the list. Be a little careful when you receive these tips. It doesn't necessarily mean this is the best way to do that. I'm not implying you should all be using the min tool or the max tool for doing something. I'm just giving ideas of how to make this work. All right. Other thing is office hours are 9 o'clock on Monday, but they're 10 o'clock on Thursdays, and I can make times other than that sometimes, but those are the easiest times to catch me for doing help with homeworks. So overview, I'm going to look at a list of different techniques, again, which are most appropriate, which are least appropriate for answering different questions, talk about the importance of stereo motion, and then give some examples of many different techniques on the same data set. So we're going to look at going from 3D back into 2D, either by slicing through or by extracting a surface, and then applying the 2D techniques on top of that. We're going to talk a lot about direct volume rendering. There's many different ways of doing this, and I'm going to walk through each of them. Some of them look like X-rays, some of them look like the brightest thing showing through, some of them look like shadows and extensions, and then give a couple of examples using glyphs. So cutting planes are basically taking one or more 2D slices that are flat through the data set. They can be along the grid axis, or they can be along some other arbitrary axis that's more interesting to look at. And then you basically put them, if you want to, in the context of 3D data sets, and then apply any of the 2D visualization techniques we've seen already on these 2D slices. So one of them is a little weird to think about, is applying a height map to one of these slices. I've actually seen it done, where you take a slice through the data, and then you make a height map showing up. You really have to explain to the viewer what they're seeing, right? Because then it's a slice of the data deformed by the data at that location. It can be a reasonable choice, but it takes a lot of explaining up to what is happening. And of course, the relative pluses and minuses of all the 2D techniques we saw before apply. So the strengths, same as the 2D techniques on the data that they display. You can look at on important axes. You can see interval and ratio fields if you use contours, if you use some height fields on the resulting thing. And if you're crossing a surface, you can see fuzzy boundaries there, right? This is something that other techniques like isosurfaces later won't be able to do. Weaknesses is they only show a minuscule subset of the data, right? And so it's 1 out of the n samples in Z. They don't indicate 3D shape of non-symmetric objects. Right, so if you have a sphere, you're going to be okay because you slice it through, it's going to look round everywhere. If it happened to be another shape in the other direction, you wouldn't see that at all. And You can also see surprising asymmetries in symmetric objects if you happen to slice them not along an axis of symmetry, right? And so that could be an issue. Then if you have a bunch of these, either they occlude each other, so you only see the nearest one, or you have to use transparency, in which case you can't really see the nearest one. All right, but you don't have to just take a 2D surface that's a straight plane through the data set. You can also take one at a particular value of interest. You can use isodensity contours at some threshold based on some surface of an object in the volume. We saw an example earlier of using a valley or ridge of maximum in those fire simulations to understand where the highest were. You can use some blood vessel extraction software, that is image analysis software, or other techniques. All right, and then again, you can apply 2D visualization on the surface. Here, the height mapping really doesn't make sense, right? Because you've got some 3D shape that you're trying to understand, and then if you deform that by a data set on the 3D shape, you kind of really lost the context that you're going to display on. And usually we're going to use isoluminant color maps if we're displaying on these extracted surfaces. Why would that be?
To prevent, I guess, what's the name for it? Where you see something that's not true, like.
Yeah, so there's going to be an illusion. What
Yeah,
particular kind of
that's what I mean.
illusion are we going to impose?
Yeah, so if you're not isoluminant, then areas will look darker than they really are, and it'll look like they have more depth than they really do.
Right, so luminous is what we use to see shape. If we put luminous contrast on the shape, we distort them. Probably the reason we wanted to extract the shape was we wanted to see the shape, right? Now, it can be the case the shape is not so critical and details on the shape are, in which case you would choose the other choice. But usually we'll be using isoluminant for extracted surfaces. All right. So here's an example of looking at a ground plane with wind vectors on it, and then kind of where the high cloud content is and where the high rain content is. And again, the fact that we're using transparent surfaces means you can kind of see where the blue one is. The white one in front just kind of pretty much disappears, and you just get the silhouettes. Here's a case where it's not so terrible to have a translucent outer surface because it's mostly setting context, and the details of what you want to see inside were important. So here, if what you really care about are the details of the bone structure, and you don't want to hide this by occluding things in front of it, this actually works reasonably well. And the silhouette gives us an idea that there's a gap over here for the side. All right, here. Is a combined example of many different slicing techniques and isosurfaces. Right? So here they're doing several different things. One is slicing along planes, and so we can see through this, that's happening. One is slicing in spherical holes, right? And another is extracting these isosurfaces. And then there's a color map that shows us the kind of lowest to highest temperature of magma inside the Earth, right? So when they extract the isosurfaces, they come out, they're all the same color. Why is that?
Same temperature.
Same temperature, it's an ISO value, right? So indeed, that's the definition of that surface is everywhere with the same temperature. But when you slice across, you can see temperature variations, right? Here they're also animating to give us different viewpoints, and each of the different slices kind of gives us a different view into what's going on. The kind of isosurface extractions show the shape of the regions, but the detail across them is seen better in the color map on the resulting spheres.
But wouldn't increasing the number of bands give you like a variation, let's say iso surface?
So could you do multiple isosurfaces?
Right.
If you did, in this case, I think they would nest inside each other, and you would only see the outer one. But yes, if you had isosurfaces and you slice through them, then you would see different colors. That's right. Here, we're only seeing one isosurface and then one slice that goes around that. Interesting thing to hear is to think about you can slice not just in planes and surfaces, but in coordinates that are better matched to the data.
Was this a good use of the rainbow color map?
There's always a better color map than rainbow. This is,
I think that actually works pretty well.
yeah, it would work pretty terribly if this was the place where you did your isosurface.
Yeah.
I'm not opposed actually to a banded rainbow color map,
Mhm.
so if they banded this, it would be, perfectly fine. It's giving you nominal data, giving you an idea of what's going on here.
Or get rid of the green.
So this is looking at dealing with the occlusion problem in an interesting way. It's saying, okay, let's see the parts of the object that we want to see. In this case, it's a protein binding site. And protein binding sites are often down and deep inside the protein. So what you care about is the thing way inside. So the outside is not so interesting, right? There's a technique that was first, I think, used in cars on major motion pictures, where they take ambient occlusion and they say, basically, I want to look at this particular point on the surface and shoot rays out, and if I can see the sky very often, I'm bright. If I can't see the sky very often, I'm dark, right? I'm occluded by other things. This is actually using the ambient occlusion not to do lighting, but to do transparency, right? And so the idea here is wherever it's down deep inside, you can see it, and everywhere else it's transparent, and you just get an idea of the outer entryway. And so this gives us kind of a very interesting close focus detail on this structure that you don't get if you just make everything transparent and see what's inside. This is a zoom in on that, and also including some molecules that would be bound inside the site to give you the idea of how these are with respect to that interior site. All right, exploded views. So here is other ways of slicing through the data in data relevant coordinates. It's a little gruesome, but it can be effective at showing you context with details in the same display.
Is this stuff from that virtual human data set?
No. This is neither the visible man nor the visible woman,
Uh,
just because I know what they both look like. I don't know where they got this particular data set. So here they're segmenting the data into kind of a halves and then into 2 quarters. And they're going to use that to kind of bring the thing apart,
Yeah.
look inside. So here you have to somehow segment it out, the center region that is the kind of spinal column and brain. If you're lucky, you can have done that using isosurface thresholding. Otherwise, in this case, I think they may have actually done it by hand segmenting the data. And now they're trying to say, okay, how can we automatically have a system that adjusts to whichever direction we're looking for, lets us see the thing we want to on the inside, but also gives us an idea of the context around the outside. And then they can change different factors, like how important is it that I see the particular thing, how important is it that things stay lined up with each other, and they're trying to kind of automatically adjust the scene. So then you can see out here, the brain parts have been removed from the volumes that are pulled out, and so you can see kind of the converse shape of inside of the skulls. Now, what particular question this is useful in answering, I don't know. And so this was a kind of a technique that they presented at a conference to show the different things they could do in their system. An interesting question to think about is, okay, when would I have this as an interesting question that the scientists wanted to look at?
Halloween.
Halloween, yeah, it's probably not the best use of someone's data. So this, I think, now they're going to hinge from the sides. All right, so you're going to see a lot of different techniques, mostly today, that are all about how do we beat this occlusion versus confusion kind of boundary that we have. How can we get the most things in the scene where they can see each other and we can see a context without just completely losing what's going on. And this is one approach at that. Okay, another approach at that is basically look based on medical illustration. The idea is if we know that we want to kind of remove a skin layer and peel apart, this is actually running kind of a finite element simulation on a mesh that's extracted from the volume data to peel away and let you see inside the bones with the kind of removed skin, or the same thing for this frog that they scanned, so they didn't actually have to kill to cut him open. My guess is he might have not been so alive in the scanner, but we'd like to think about it. All right. So, extracted surfaces, many different ways to extract them and show them. So the strengths, again, are the same as the two techniques that we saw previous week. You can see interval ratio fields. This shows you 3D shape of even non-symmetric objects, right? So you can pull out a head with ears, all kinds of arbitrary shapes of the magma inside the Earth, and you can see those pretty well. And seeing 2D shapes in 3D is what we're very good at, right? And so it's very, very effective. Doesn't show fuzzy boundaries well, right? And so if you extract a surface, you don't know what the thing's doing perpendicular to the surface. It can emphasize noise in any case, and if you pick a particularly poor level, you get this really interesting feature that doesn't make any sense, right? This is kind of like what happened with contours in 2D. With the DNA, if you picked a strange value, you got a really interesting feature that wasn't data relevant. Well, here you get an interesting 3D feature that's not data relevant. It's a minuscule subset of the data. Now this is a plus if this is the that subset of the data you cared about, right? If you're asking what is the surface of this bone and is it broken, then extracting only the surface of the bone is exactly what you wanted to do, right? And then again, you can these either occlude each other or require transparency. So either they have to move them out of the way of each other, in which case their kind of relative location is not the same, or they hide each other and you can't see them. So one thing to think about is a hard, distinct boundary useful for this particular visualization task, this particular question that it's trying to answer?
It seems like one strategy we keep seeing is where they will show sort of an opaque, a non-transparent outside, and then the same thing with part of it made transparent. So you can't really tell what the shape is over here, but you can look out to the side and, oh, that was kind of a lumpy bit, and so I guess it's sort of, with the video you could sort of transition between those, but for static images that seems like a trick that we see over and over again.
So you're saying that we've got a transparent thing here and then the opaque version of it over there. So
Yeah. So you got like the face, and then over here you got it with all the skin ripped off or whatever, and or a piece cut out of it or whatever. So,
Mm-hmm.
yeah.
So multiple views of the same data exploded could do that effectively. That's right. All right. So again, we know about making translucent things perceptible by adding texture features. You can either replace translucent surfaces with opaque bands, strokes, patterns of opaque texture, and we're going to go through some of these. And it turns out that adding stereo and head tracking is better than the sum of the parts for this. So there's two things you can do in terms of texture, and we're going to see those, but the motion can really help understand what's going on in these 3D shapes, especially with kind of semi-transparent objects. All right, so basket weave here is an example of taking strips of the surface and making them opaque, and then the other ones transparent. And so here we've got two nested spheres, and you can see one inside the other. This kind of regular grid texture helps us perceive the surface shape as well and gives us kind of a good representation. But if you take these strips and make them into 1D lines, suddenly you don't get to see as much information, right? So a couple things happen here. One is these lines are unlit, so that means that no matter which way they're facing, they don't get brighter or darker, right? And there's high density in these lines, right? And so they're very much overlapping, and so we can't get an idea of which ones correspond to which as they go around. It turns out that if you had normals to change the lighting, this would give you a better shape. And if you had stereo or motion, you would start to disambiguate which line was which, and this would be a more effective technique. So this one with the kind of flat surfaces and regular thing works even in a 2D display. This could work in 3D, but could be made better with lit lines and lower density. All right, so this is a case where I'd say, okay, what we're going to do is put little spheres all around the surface. And so here they're lit spheres, but the problem is the spheres are lit individually, right? Each one is kind of lit by the light. It's not based on the local surface normal, right? So this doesn't give you an understanding of the local surface shape, and so this pretty much falls apart in terms of understanding, what these overall shapes are. If you had these points lit by the local surface normal, you would start to get an understanding of shape from shading, and this could be a better way to do that. All right, so we saw the curvature-directed strokes before. So this is kind of the opaque outside and inside, transparent outside opaque inside. This is curvature-directed strokes along the line of the first principal curvature, and then these are kind of in oriented random directions. And you get a little bit better idea of the outside shape with local curvature.
How do you determine the direction of curvature? Is that like a PCA or something?
So the question is, how do you determine local surface curvature? So it turns out that it's incredibly hard on a polygonal data set to reliably determine the local surface curvature. There's, dissertations on how do you do that perfectly. But the basic answer is, you look at the local the Hessian of the surface, and you can say, okay, is this, bending down, bending up, and it gives you an idea in two different orthogonal directions. You look for the direction of maximum curvature, and that's the first principal curvature, and then the minimum will always be perpendicular to that. And so you use Scalar or some library essentially to compute this for you. I think is what it has. There's probably a principal direction curvature filter in VTK that you can use to generate.
I don't remember what it's called right now.
All right. Another approach here is was taken by Penny Reingens, is to say, okay, we're going to put an even texture on the surface that's got kind of holes in it. This is kind of like a basket weave for those chairs you would sit in, right? And so this is showing you kind of a hexagonal tessellation where the outsides of the hexes are opaque and the insides are completely clear. And so you can see an outer surface, an inner red surface, and then the molecule inside. In motion, this is actually fairly effective at understanding what the 3D shape of this is, whereas even in motion, the pure transparency, you don't have any idea from front to back. The relative motion of those features and the speeds gives you an idea of the depth pretty effectively. So this is kind of the converse of that. This is saying let's put little patches on the surface that are round, and so they're opaque where the surface is, and these are then lit by the surface normal, not all the same way as if they were spheres. So this is kind of equivalent, but a lower density to this earlier sphere example, but we put them on the surface and light them, right? And so this gives you an idea that there's a kind of a purple surface and a blue surface. You can get an idea of which one is in front of and which one is behind the other a little bit. It turns out you do a much better job if you have local crosses on the surface that are curvature directed. We're going to see those later in the multivariate lectures. And the homework too shows you how to do the little crosses. Yep?
The thing is for example, you're telling once you have detected the surface or the type of it, the structure of it, you go about doing these things. And for example, if we are looking at modeling the skull, we exactly know how it's going to look at. But take that in contrast to iron protein. So you are not aware of the structure and you have just some data. So how do you go about saying that this is the structure which I'm going to use and go about then applying?
Right, so the iron protein, for example, you would do an isosurface extraction at 2 or 3 different iso levels, and then you would treat each of those surfaces as a place to splat down these local disks, and this would give you kind of a blue isosurface, a pink isosurface, and maybe a third green isosurface.
But if you have a raw data and it says that this is an iron protein, and
Yep.
then you have to ascertain this is the structure for that.
Yep.
And then you go about trying to do extract isosurfaces and things, right?
So the isosurface is what would tell you what the structure of it is.
Yeah, but ISO what? What do you need to know ISO what? Right?
That's right. In the case of the iron protein, it's isodensity of electrons.
Okay.
Yeah.
So you need to before you can ascertain the structure of that data, you need to understand what data it is, and depending upon that, you have to.
So I'm trying to think about to what extent does it matter what kind of data you're looking at.
So my
If it were partial charge, if it were density, if it were density of electrons versus density of kind of skin or bone, I think you could still isosurface any of those things and get some idea of what the shape was at that value. Now in the iron protein, an iso value surface may not make any sense, right? Maybe it's so highly noisy and such a gradient everywhere that doesn't make sense. If you pull the surface and it's just a chopped noise, then yeah, that didn't make sense. There's a lot of places inside a person that a density value doesn't make sense, right? Halfway between skin and muscle, you get this very complicated, useless shape. Whereas at the bone boundary, you get a good shape, especially with gradient. So you're right, you do need to understand something about the data to know where you would set these values, or if it's an appropriate technique. But the isosurfaces and slicing are fairly generally useful, and they pretty much do the same thing independent of the underlying data set. All right. And we've seen again that animation is a useful way, and again, kind of torsion pendulum rocking, which is not what this is, or kind of spinning completely around, give you two good displays of that. But it turns out that head tracking is very useful because the object seems to stay put. Stereo is very useful when you see both with both eyes. And head track stereo is actually better than the sum of those two parts, right? So if you use head tracking, it's about this good. If you use stereo, it's about that good. Off the table, head track stereo is way better, right? And this is kind of what we have as we look at real objects in the real world, so I can believe that that would be very useful.
I think this one should be an anti-pattern because the texture on the surface makes the inside shape on the one on the right look like a lazy boy, to me at least, and it clearly is not on the left.
So you're saying you're hiding this feature here?
No, the whorls on the two, sort of where the arms of the chair would be, make it look like the thing in the inside is sticking out more than it actually is, which it's not, in fact, right?
So you're saying we're getting distortion on the
Maybe
inner surface and the
color,
outer.
having a different color for the thing on the inside so you could distinguish that from the texture. Maybe,
I like
but,
that.
I just don't like the swirly texture stuff on the outside. I think it's confusing.
Well, the good news is it's, so, again.
But it does
in
let
most
you see that
cases-
lump on the outside.
In most cases, there's a trade-off, right?
Yeah.
And so what you're seeing is that here. This is really, really good at showing the inside, and you can't see the outside. This is not so good at showing the inside, but way much better at showing the outside.
Mhm.
And unfortunately, the way the visual system works, a lot of what you're going to be doing, you'll see in these homeworks, you're already experiencing this, is, well, I can put this in there, but that bumps that down a little bit. How do I find the maximum? Well, I don't know. If I cared mostly about the inside surface, then indeed the one on the left is the one I want to care about. If I care about the relative depth between those in front and back, then the one on the right is better. But you're right, we could do even better by making the inner one a different hue so that you could see the differentiation between the swirls and the things on the
Yeah,
inside.
yeah.
All right, so now we're going to talk about direct volume rendering. In most of the things I talk about in the class, we don't care about the implementation. In direct volume rendering, the way you render and the parameters you set affect the final outcome, so we do need to understand what the direct volume rendering pipeline looks like. So a bunch of terms to start with. A voxel is a volume element. It's like a pixel, but they're 3D, right? So if you chop this room up into sugar cube sized objects, each one of those things would be a voxel. It's the basic unit of volume data. So to get values that are not at voxel centers where you sampled, so you can draw a surface, you basically use interpolation. And so what that means is you kind of smoothly move from the values in this sugar cube to the ones in the neighboring sugar cube. Usually it's trilinear interpolation, which just means you just uniformly move them along a line here, and then along a line here, and then you take the middles of those lines and do the line there, and the two planes and do the lines there. So you do 3 linear interpolations to get the individual values. This is going to produce the same kind of star artifacts that we get from bilinear interpolation on a 2D surface, but it's the one that's supported and easy to do in hardware. There's an over operator for compositing, so the whole room is full of sugar cubes. Somehow you have to render the far cubes and the nearer than the nearer. How do you composite them? And there's an over operator that we're going to talk about later. And then the transfer function, which comes later. The gradient is kind of how the temperature is changing in this room, how rapidly and in what direction, how the kind of density is changing inside my head, what direction and at high magnitude, and so we'll go through that. So the gradient is you take a 3D scalar field, you take its gradient, and this is a 3D vector field, right? And so it points towards the direction of a maximum increase, and the length of an arrow, or length of the gradient, the size of the gradient to the local point is how fast the value is changing, right? And so this is kind of a gradient going inside. This is kind of a slice through. If you had an exponentially falling off scalar field, so it's brightest in the middle and it falls off as you go away. Then as you're at the edge of the slice, towards the middle is where it points in a 2D slice. These are vectors pointing towards the center, which are kind of all going around in 3D, pointing at the same center. So the gradient magnitude in that case is higher near the middle, it's lower near the outside.
So it's just The derivative, the first order derivative of each
It's the
element?
first spatial derivative of the density value, that's right.
Okay.
All right, so the basic idea in volume rendering is you integrate as you go through the volume, either backwards or forwards. We're going to talk about it in this case as we start right from the eye and we sample the first sugar cube and the second sugar cube and third and the fourth. The idea is that every voxel contributes to the image, right? So you're not hiding anything, whereas if you do an isosurface extraction, you're hiding everything except for values that are on the surface. There's no intermediate geometry, so you can actually do volume rendering faster than surface extraction than rendering in some cases. Even if what you render looks like a surface, you can render it faster in volume rendering, so sometimes it's used just for speed regions. It's more flexible than isosurfaces. By picking the transfer function, the over operator, and gradient, you can actually get many different results. And so we're going to see some of these as well. All right, so again, we're starting with this sphere that's very high intensity in the middle, falls off as it goes away in 3 space. And we're looking here at 2 different transfer functions applied to this same data set. All right, so here the transfer function is a little bit weird. It's not in 3D space, it's in value space, right? So here's the minimum density, greater and highest density is here, right? So this says anything that is the densities in this little range here is completely opaque, and everything else is completely transparent, right? So it looks like this very interesting little golf ball-y thing. You should ignore the kind of stair-steppy things on the golf ball. Those are actually the sugar cube boundaries, right? And so there's techniques to remove those sugar cube boundaries from the rendering. But in this case, it's basically showing us that all the little sugar cubes that are at that density are opaque. So this is basically all the ones that are at some particular value around the outside of the sphere. It's actually hollow inside, right? We can't see that because the sugar cubes here are blocking the things behind. So if you ever have complete opacity, you hide everything behind that value. This is the same data set, excuse me, with a different transfer function. So here, things inside are completely transparent. The things outside have growing transparency up to some level, and then they fall off, all right? So here in the middle is completely transparent. So why is there kind of a brightening around the edge? It's not a visual illusion in this case. There actually is a brightening in the rendering.
Is it just because the outer layers aren't completely opaque, they're somewhat transparent?
That's true. And that's also true here.
And we're looking straight down a bunch of voxels that are at that intensity, so they stack up as you
Right.
pass through.
Yep, so this is like looking out towards the horizon. You go through a lot more air on the way out of the Earth that way than you do straight up, right? And so the air itself that's near there is in fact brighter, and so we're adding up a bunch of bright voxels along there. Whereas here we go up the transfer function on the way in, down the transfer function on the way out, and that's the brightness. At the edges we hover around this area more, and so it accumulates more brightness. All right, good. So it turns out you can separate the transfer function and the color, right? So the opacity and the color, and so you have kind of a color transfer function and opacity transfer function, and we see that in pair view as well. So this is kind of a mixture. It's the ramp thing plus a kind of bright inner side, right? Again, these black squares are rendering artifacts. Sorry, the people who made this didn't do a perfect job. So this has the combination of both of these 2 earlier ones. There's an opaque inside and this thing on the outside, and they're both in the same image. But now, if you kind of bring green and red down in the color of this inner thing, it's an opaque blue object inside kind of a white surround thing. So you can separate different regions of the space based on density values with colors. This is adjusting now the same transfer function in both these cases, but we're adjusting the color mapping, right? So here we've got the same blue thing, but we've got a fall off of red and green around the outside. And so here we kind of get a pinkish glow around the boundary and a blue thing inside. And so you can separate the how hard it is to see through something from what color that something is. And you kind of got a very high dimensional choice here, right? You have like 256 values for each of those. You can arbitrarily choose them.
What is this a picture of?
This is a picture of an exponentially decreasing density that's spherically symmetric. So in the middle, it's very high density, 255, and then it falls off to 0 outside.
In pair view, is this so that when you're editing the color map, you've got that graph where you can kind of, it seems like you can click and drag values. Is that what this is? Yeah, that.
All right. So in pair view, this is the opacity part,
Okay,
and this is the color part.
okay.
And so they don't have exactly the same mapping here, but so this, you can, if you pull this guy down, and you put another one and you pull it up, you would have something that looked a lot like this kind of sharp boundary here.
If you accidentally click on that thing a couple of times, can you undo it? Because that happened to me and I just had to close it out and open it up again.
Uh-huh. Does Control Z help you?
No.
Nope. So, yeah. Don't
Okay.
save before you close, yeah.
Yeah, okay.
The other thing is save state is very helpful in pair view for two reasons. One is because it helps you undo things if you, but the other thing, pair view crashes a lot. Right? You're gonna have, if you haven't noticed this, you're gonna notice it. And especially unexpected times, like undo the thing that I just did. Okay.
If you remove the counter value, if you press the
You can
minus
sometimes
button-
run out of memory and kill it. Yeah, depends on the counter value. Yeah. It's so. Previous versions were more stable. So 4.1, if you find a thing that crashes all the time, you might step back to 4.0, and as long as it has the features you need, you might be happier. I go with the latest one because it's got the best transfer function editor, and I think it maybe starts to have some gradient-based things in that. And so we'll look at that. All right. Then this, you can grab these beads and move around the color of this thing independently of the opacity.
So what happens if you click and add more points and if you change that?
Yeah, you can do arbitrary things by putting a bunch of points in there.
So,
Why would you want to do that? Yeah, so we'll look at some examples of why you might want to do that. Yeah. But normally you don't want to do that. You don't want just some arbitrary thing. Although if you want skin and bone, two different colors, you might do something like that. Right. Now, you probably want the skin not completely opaque, or you would never see the bone inside unless you slice through. Different choices. All right. So now that we set a transfer function, we kind of describe the characteristic of every voxel, every sugar cube in the room, how opaque it is, and what color it is. Now the question is, how do we combine these when we put them together onto the picture, right? So if what we care about is where is the highest density anywhere in the room, I don't want to miss it, then what you do is you take the maximum voxel you got through on any ray, and you just bring it to the front, and you show it with its transparency and its color. And that's maximum intensity projection, or MIP. Then there's X-ray-like, which is like if I want to shoot something through here and know how likely is it I'm going to run into some density, then this basically sums up, or averages, same thing, the densities from the beginning to the back, and gives you an idea of the integrated density you've gone through at any particular location. This is like an X-ray, right? And so for years, CT scanners were almost always used to produce X-rays from different viewpoints, because that's what the physician was used to seeing, and they wanted to see what an X-ray like was. And so basically you sum up the whole thing, and then you can clamp it. The composite is basically saying, okay, we're going to make things that are more opaque hide things behind them that are behind them. Things that are less opaque don't hide them as much, right? And so this is basically saying, okay, we're marching through D0, D1, D2, D3, so the value is DI plus the value at the next one times the inverse, right? So I take the one that I'm looking at here and I put in, if it's 90%, 90% of the color of this pixel comes from this voxel, and 10% comes from all the ones behind, right? And then recursively we do this. And so the first one, if it's very highly opaque, it hides everything behind. If it's not, then it shows through what's behind. And this is normally what people think of as direct volume rendering. Is the opacity depends on the kind of, how much the density is in the local region, and then they have that way. All right, so setting transfer function turns out to be challenging, right? And so here is if you say, well, we're just going to take a ramp so that higher things are more, lower things are less. Look at this head, we should see something. No, we don't, right? We see this. So there's an ear, there's a nose, There's something going on here. So this is the same thing as I were like looking at the edge of the earth with a lot of air. So even the stuff in front, even though each one is maybe a little bit small, it accumulates pretty quickly and hides this. Well, okay, let's make a little triangle. Oh, it looks about the same. Why does it look the same? How could it possibly look the same?
Maybe there's not that much on the ends.
Well, this highly kind of opaque stuff was already embedded inside the goo. And so it didn't matter how you drew the stuff inside, it was already inside the goo. All right, well, let's make the triangle a little narrower. Wow, now it looks like this. What the heck is going on? So here, we've pulled the values down, so pretty much only inside bone density is anything opaque, and now we only see bone. Everything else is completely transparent. Well, let's move the triangle over a little bit. Well, now we see the skin, right? So now what we've done is we've moved out of the bone density region into the skin density region, and we see this really interesting stuff happening down here. This interesting stuff down here is called beam hardening. This is basically the fact that they're clamping the values. You can't get many data values because there's so much in the middle filing blocking that the equations they use to invert the Fourier transform just fall apart, and you get wrong answers around there. So that's an artifact of the scanning. And you get this interesting shadow up here, which is where they had a strap to hold the person down, to hold them still during the scanning, happens to be about the same density as the skin, right? And so, again, it's not a spatial thing that you're measuring here with the transfer function, it's a density space thing. So things that have similar density will show up in both of those images. So a lot of the work in volume rendering is how do we figure out what the transfer functions are? How do we set them? So one way, if you're using a CT scanner, you can actually calibrate it by putting a bag of water inside there and measuring the density of the water and then doing everything in Hounsfield units relative to the water, right? And we know what the range of bone is, and we know what the range of skin is, and we know what the range of muscle is, and air. So you can actually say, I want to see the bone on this patient, I want to see the skin on this patient. And it's not a strong thing. People's bone varies a little bit, and within your own bone it varies a little. So you get these kind of probability density distributions that show you this is probably going to be the bone, this is probably going to be so forth things, and you can just pull out the bone or the skin, and you're done. MR scanners, on the other hand, even locally within the scanner, will have deformations due to field irregularities. From one scan to the next, they'll be different, and so you have to kind of tune these a little bit, and you can't just pick individual ones. Transfer functions and volume rendering itself is a little bit unintuitive, so you might think, okay, if I want to look at this down here, if I pick a particular transfer function like this, I would expect a disk, right? Sorry, let me back this up again. Again, same spherical thing in space, right in the middle, going low towards the outside. You might say, okay, I'm going to just pick out the edge, and I expect to see the edge. But again, it's not a spatial thing, it's all in volume, and so what you see is the whole ball around the outside. Right? So you're not slicing through it, you're kind of slicing through the space of densities, and that's going to give you kind of a spherical rendering of the outside.
So if you push it to the right, you'll see the interior layer.
If you push it to the right, you'll get a smaller and smaller ball in this particular data set. That's right. If you push it to the left, you'll get a larger and larger ball because you're picking the region of density that's different. That's right. All right. So one way to pick a transfer function is I can't tell you what I want, but I'll know it when I see it, right? And so the idea is, in this case, NIST came up with an approach where you would put a 2D slice on and pick a place on that slice and say, I want to see this stuff, right? Or take a pen through space and say, I want to see all the stuff that's like what I'm pointing at right now, right? And so it would figure out what that meant. And so this is a two-dimensional transfer function. All right, what's that mean? So this dimension is density, like all the ones we've been seeing before. This dimension is gradient magnitude. Okay, so what's that mean? You compute the gradient of the volume. This gives you, and you take the magnitude of that. How fast is the density changing here? So at the edge of the bone, the gradient magnitude is very high. Inside the bone, the gradient magnitude is 0. The density at both those locations may be the same, right? And so you're basically saying, okay, I want to segment the stuff that looks like this. So locally, it computes the gradient and the density itself, picks a region in this space, and extracts all the stuff that kind of matches that region, right? And so then you can kind of get more samples, paint on, okay, I want more like this. And if you always are on skin, it'll know which subset of the magnitude, which subset of the density you want to pick. pick a region in this space and kind of automatically extract the local region that you cared about, right? So this is really cool. This is like, I want to, as you move around, all of a sudden you'll see the bone edge, then you'll see the middle of the bone, then you'll see the skin, then you'll see the muscle as you kind of encounter it with and so it's doing kind of feature extraction in the space of gradient magnitude and density. All right, so here's an example of doing that, moving the pen around inside this data set. And this is, kind of where in density space and gradient space are, kind of points that are around your pen. And so it's extracting this two-dimensional transfer function, and we're seeing different features show up on the right. Now in this case, we've done something I haven't told you about, which is illuminating the surface as if it had a gradient, according to the gradient, so that you get lighting in the volume data. Nothing that I've described yet would do lighting, but this particular display has lighting, and I'm going to talk about lighting next. And that's why this looks like a bone lit, from the skull from side, not a glowing white thing where all the bone is. All right, occlusion spectrum.
This paper presents the occlusion spectrum of volumetric objects for classification and visualization. The occlusion spectrum represents the distribution of intensity and ambient occlusion of the different voxels in a volume, as shown here for several data sets, including CT, MRI, and simulation.
So here what they're trying to do is say, what is the density locally?
With the occlusion
and
spectrum,
how does it change as I go away
we can
from
build transfer
myself?
functions that help us isolate features such as a tumor in a brain MRI, separate overlapping intensity values in CT scans.
And so this is going beyond the two-dimensional transfer function, saying locally in space, not just at my location, but around me, when do I encounter high-density things, right? And so if I'm far away from them, I get one transfer function. If I'm nearby them, I get a different transfer function.
Or separate organs in a biological CT dataset. In this example, the user attempts to isolate a meningioma using a 1D transfer function. By dragging the blue curve on the right, the user can select the desired occlusion level for a particular intensity value, revealing different structures. In this example, we classified a breast CT scan. A 1D transfer function helps us visualize the tumor, but at the expense of reducing the opacity and losing clarity and context. With the occlusion spectrum, shown here as a 2D scatter plot, we can obtain a clear view of the tumor while retaining important contextual regions. By creating and dragging 2D widgets in this space, the user can highlight the tumors and have an unprecedented clear view of the vessels that fit them.
All right. Volume down.
We demonstrate the technique proposed in the paper by designing a semantic model for CT and geography data and two-dimensional transfer functions. The 2D transfer function is specified based on intensity and gradient magnitude. The basic editor that we used for creating transfer functions supports different types of primitive shapes, such as trapezoids, paraboloids, and quadrilaterals. In the first step, the structures contained in the data are identified. In our case, these are bone structures, brain and soft tissue, skin and cavities, and blood vessels. A visualization expert, supported by an experienced physician, creates an initial template for the transfer function. This is achieved by generating different primitive shapes in the editor and by aligning them with structures found in a 2D histogram. This way, the visual appearance of all the structures of interest is specified. We create transfer function primitives for the bone structures, the skin, the blood vessels, and finally for the soft tissue. In this example, we have used only a single primitive for each structure of interest, but if necessary, multiple primitives may be used as well. The result of this first step is a transfer function template that represents all the relevant structures contained in the data. In the second step, the template is adapted to a collection of reference datasets. This collection should statistically represent the possible range of data for a specific clinical purpose. We suggest using as much reference datasets as available. The transfer function template is adapted to each reference dataset, and the parameters of the transfer function model are stored for each instance. Adapting the template to an individual dataset requires to move and modify the existing primitives to realign them with the slightly different structures in each individual histogram. In the third step, the set of reference transfer functions is used to finally create the semantic.
What are these blobs in the little window that they're fiddling with?
These are
the
region
gray-
selectors.
No, I got that. What's the image that's in there? There's like a
Oh, so
they call it a
so-
histogram.
Yeah, so what they've done here is they've taken every voxel in the data set and they've splatted it into its density and its gradient magnitude. And they
Okay.
sum up those values. So this is like an X-ray of the projection of these this 3D data set into 2D. So this is a 2D visualization where we're looking at basically a brightness that depends on darkness that depends on the number of voxels that fall into that category.
Okay.
Yep.
There's probably a lot of work on this, but it seems like you could do like some sort of automated segmentation, like model this as a mixture of Gaussians or something and figure out the mean for each different texture and then just automatically find those transfer functions.
See, now you've got a new paper for visual texture. Excellent.
I got a PhD maybe.
PhD. He's already got that.
Oh.
Yes. All right. So another approach, which we saw a video of earlier in the class, was what you see is what you get volume rendering. And here, what you do is paint on the image, and it looks into the image with the current transfer function, decides what you're seeing there by what's the kind of first opaque thing, adjusts the transfer function of that region in transfer function space to, for example, change the color, right? Or to make it more transparent, or to make it more opaque, or to apply edges. And so here you basically draw on the image and put this in. So, this was my dream thing to get put into PeerView, and we put it in the Visent thing, and it was like way too hard for a summer intern to do, so it didn't get done. But one day we hope to have this kind of available to users. This is you don't have to think about what you're trying to do. You're kind of you're drawing on the surface itself what you do. All right. So how do they do volume rendering? Right. So we know kind of what they're trying to compute. How do you compute it? There's a couple different ways. There's image order, which is going from your eye through the image, or there's object order, which is splatting and texture mapping. So I'll go through each of these. And so basically, this was raycasting. Says, okay, I'm going to start from the front. I'm going to march my way through the sugar cubes in the room, and I'm going to kind of apply this over operator. So one that you might apply is the maximum, right? So I might say, I look at all the sugar cubes, I pick the highest density, and I bring that one to the front, maximum intensity projection. So that would be kind of here, and that's what this image looks like. I might say the average, right? Like an X-ray, sum up all the way through, just add them up, about 2. I might say, I want to tell how far into the image I went before I got to something that was 30 or greater and show that, right? This is kind of showing you a depth map of the kind of high values in the image. Or I might do the compositing, right? So I'm going to add up, I'm going to take however much is left over. The first one was 10%, so 90% of the data comes from the rest. The next one was, 20%, so approximately 70% of the data comes from the rest, and I add it up along the way. Splatting says, okay, what I'm going to do instead is take all the sugar cubes from back to front and throw them at the screen, right? And I'm going to do the same operator, or the inverse operator for the over, where I say, okay, now I'm going to kind of replace whatever's there with the amount that this cube hits, whereas before I was reserving kind of some space for the cubes that come behind. And basically, the question here is, what area on the screen do I put this, right? And so if you just did points, you might have a voxel grid that, it kind of has missing black regions in between where you had no data going there. So you might do, squares that are about the same size as a projected area of the thing. You might do Gaussians that are about the same size, depending on how much compute power you have. What kind of splat you do is kind of important to the rendering. The basic idea is you go back to front, you throw them all at the screen, you add them up, and you see what you get. Texture mapping basically says, okay, what we're going to do is exploit the fact that we have hardware in our graphics cards that can do very quick rendering, and we're going to put a bunch of planes into the world, and we're going to color those planes according to the density values they pass through, and then we're going to just render those planes back to front, right? So this is very much like doing splatting, but it's just doing splatting with the graphics hardware. So it's kind of the same calculation, but it's using that kind of fast stuff. So if you click on GPU rendering, this may be what your volume renderer is doing. Since then, they actually now do raycast volume rendering inside the graphics hardware, so all bets are off. So there's a couple ways you can do this. You can line the planes up in data relevant order, right? And then you get these weird kind of corner effects along the edge, right? Where you're seeing past one plane to the next one, and at the boundaries you get these weird artifacts. Or you can do kind of screen-oriented planes where you move the voxel cube around and you kind of slice it this way. And here, what happens is you're seeing the planes clip through the volume at whatever angle they go through it, and you get the artifacts around the edge. So as you're moving things around in ball view or moving things around in pair view, you'll sometimes see weird artifacts that you'll let go and it'll kind of look better because they've reduced the number of planes to make it fast and increased the number of planes to make it look better. And these artifacts are, of course, worse when you have fewer planes to look at. All right. So what I haven't told you yet is how they do lighting, right? So how do we get those lit skulls in the ones that we saw in that video before? Well, what you can do is say, okay, I'm going to compute the gradient magnitude, and I'm going to use the direction of that gradient as my normal direction to a surface, and I'm going to illuminate this as if it were a surface, right? If you're really fancy, you can use the magnitude of the gradient to say, am I really a surface or am I not really a surface? And if I'm not have a high gradient magnitude, then I just use kind of unlit compositing. But if I have a high gradient magnitude, then I use lit compositing, right? And so, and again, the direction is the way kind of towards lower density. Right? So the outside of the bone, the gradient will point in towards the bone. The opposite will be away. And then you just do lighting the same way we talked about in terms of Phong shading or kind of the specular term plus the diffuse term. In this case, the ambient term is just the additive value coming in from volume rendering. All right. You can do shadows, right? What you can do is basically I'm at a place in the volume, so I know where the light source is. I'm going to just do density accumulation to the light source, right? How much density is between me and the light source, and I can apply a transfer function to that or not, so that things that are over there will cause shadows from the light source, right? So the lighting is, a little more computation up front and during rendering. The shadowing is yet more computation during rendering, but can look better. You can add color, right? So we saw that before. Depending on which regions you want, you can say, okay, this region is opaque and yellow, and this region is opaque and white, and so we get skin and bone, or liver and arteries and bone. All right, so an interesting question is, what's the best way to do it if you could do anything, right? And so we're going to see this as in vector fields and see this in 3D volume rendering here. So this was a study that was done back in 2011 to look at, okay, here's a bunch of different advanced rendering techniques you could use on volume rendering and which one is better at which particular tasks. And so this is the Phong illumination. So this is basically saying I'm going to no shadows, but I'm going to do the local gradient, I'm going to light it as if it were surfaces, and then this is more and more increasingly complex ambient occlusion, different rendering techniques, right? And so they said, okay, we've made a volume renderer that can do all these, we're going to test this with user studies to see which ones work the best, right? And so this was, how much did the user like this, right? And so this, they ask each person, okay, here's one on the left, here's another technique on the right, tell me which one you like better. And this is ranked from more preferred to less preferred, right? So the most preferred was the Phong model. The next most was the half-angle slicing, and then the more complicated ones were less and less preferred when you just ask people, how do you like this volume rendering, okay? So then they asked the question, how well can you do a task with this volume rendering, right? And so they had different tasks. One was, tell me the sizes of these two objects in this scene if I use these different volume rendering techniques. And this was kind of the correctness. So again, better is on the left. And so the colors here match, right? So Phong has gone from the most preferred to the least performing, right? So if you want to ask shape, they like it best, but they don't answer the questions very well. If you're asking about shape sizes, this kind of directional occlusion shading was the best of the techniques that they tried, followed by the shadow volume propagation. Then they asked, what's the relative depth of these two places in the image, right? So which one is closer versus near and how much farther it is. And so again, Phong was kind of down with the poor performers. Directional occlusion shading was the best for this question as well. And so then they asked, okay, what's the absolute depth perception error, right? Tell me how far it is to this location in the scene. And so in this case, smaller is better because this is a graph of error. So here the half-angle slicing was the best. Directional occlusion was still pretty good, and Phong was down again with the poor choice. Now you notice the colors change for each of these three things, right? And so, if it's preference versus performance, there was kind of an inversion. That was the major thing. So that says basically what looked best didn't perform best. And so if you're designing a visualization for your client and you get one that looks best, it may not be the one that performs best for what they're asking the question, so you should test that against some actual data to see that it's useful. The interesting thing is, the second one is the best technique depended on the task, right? And so, we kind of knew this from thinking about it, but it shows up again empirically when you do user studies. And so my dream is to have this kind of online, all the time Mechanical Turk running, where they're testing the best techniques, the best questions, and we'll rank them and we'll see the best. Someday maybe we'll see that happening. If you want a dissertation topic, that would be another interesting one to look at.
So which of those looked most like a good illustration that you would find in the textbook? Because I would think that since we've been drawing these things for hundreds of years, we've gotten reasonably good at it.
That's a very good question. So you might ask which of those looks like the Netter textbook, right? So the Netterly rendering. The answer is none of them, right? So Netter uses contour shading around the edges. So this is why there is no user study that's the final user study, because you can always ask, okay, well, here's 5 more questions and here's 10 more techniques, right? So that's an interesting question, and we don't know the answer. For molecules, there's much better rendering styles than these kind of realistic ones for understanding shapes, and so, yeah. All right, so now we get a little more exotic, and so we showed some of the examples of this in the kind of the pain lecture, and so here is, if I want to see gaseous illumination of CT, color map gaseous, or silhouette and boundary enhancement. So this silhouette and boundary enhancement is more like what Netter would do with the anatomy text, is you'd see the edges more clearly, you'd see the texture more clearly because he would highlight those. And so for what you wanted to see were edges and understand detailed structure, then this is a transfer function that looks not only at the local gradient and magnitude, but the dot product between the view vector and the gradient in the gradient direction, right? So if you've got a gradient that's opposite the viewing direction, it highlights and kind of does a dark light transformation on that to make a very sharp edge there when there's something going across. Here's different exotic transfer functions, tone shading, color volume rendering. It just gives you different views of this same data set, and the question is, what question are you asking that you want to do? This is one of my favorite transfer functions. This is a tomato transfer function. This is that same boundary and silhouette one, right? So this is a tomato. So for computer scientists, what we do is we don't have any data, so we take our tomatoes, we stick them in CT scanners, and do some volume rendering. And this is saying, okay, I wanted to look at the silhouette. So here we're seeing the boundaries and the kind of meat of the potato much more clearly, but the overall shape not as clearly, right? And so which question was better depends on, which was better was depending on the question. But this again is showing you some structure that really is there in the tomato. Now on the other hand, This is going to highlight noise, right? And so you're going to see a lot more noise in the data set because you're looking at these small gradient dot products, which will be changing rapidly in space.
You also seem to have discovered a seedless tomato.
A seedless tomato.
Where are the seeds?
There are seedless tomatoes, aren't there?
Yours doesn't have any.
Yeah, not my tomato. But you're right.
You didn't seem like a tomato kind of guy.
All right.
Whoa.
This is importance-based volume rendering. This requires some segmentation, some pre-idea of what you care about. And this is, in this case, I want to care about the liver, and then I care about the spine, and then I don't care about anything else, right? And so this says whenever the liver is on the screen, it includes everything else, even if the thing's in front of it. Spine does the same, and then kind of everything else does that. And this lets you see the context, but the context never hides the thing that you're trying to look at. You can also do that with kind of a screen door-based transparency or kind of a highlighting around in white. This is the same thing done with the kind of the airway, and then the bone, and then the skin, right? And so whichever way you look, you're going to see the airway. The bone's going to include that just a little bit, but the skin is always getting out of the way. So it provides context around, but you can see inside, and it never hides what's inside. All right. This is Superman X-ray vision, and so this is looking at the ball and the socket of a shoulder joint to see kind of how much damage there was on this poor person's shoulder. Why did it stop? All right. And so this was David Borland's, it started out as a project in this class, became his dissertation project, became patented, got licensed to Siemens, and so if you get scanned in the hospital, they may be looking at your shoulders with this technology. So the idea here is automatically remove the stuff that you didn't want to see so you can see what's behind. And so here, for example, is looking at a tear in somebody's shoulder. Normally this part is supposed to be connected to that part, right?
Ow.
Yeah. So in this case, you're inside the bone. Normally the volume renderer would show you the bone. This, whenever it gets to the contrast, deletes everything in front. So it's basically saying, whenever I get to the contrast, I want to see what's on the other side of the contrast. If you start out in contrast, which is the liquid they squirt in the joint, then you just see the far sides of the render. So this is kind of a mixed mode rendering. So skin is done with one technique, the bone is done with another technique, the blood vessels are done with a third technique, right? And there's a bunch of examples here on the slide that show you different mechanisms of this, and each of those highlight, the skin versus the bone versus the blood vessels in different ways. Same thing happening here with the head, the skin, the blood vessels in the head. This is a mixed mode rendering that doesn't work pretty well, it's quite as well. You get some silhouette going on, but again, the pure transparency hides the shape that's going on. All right. So the characteristics of direct volume rendering, there's different classes of them, right? It's not like you can say direct volume rendering is like this. Well, the X-ray ones have one kind of set of characteristics. The surface-like ones look just like extracted surfaces. They may be faster to extract than surface rendering. Physically based with soft edges, and custom exotic ones. And so this is the case where there's a lot of things out there. You can try different things and see what's going to work best. You can get some ideas, but there's no overall thing. So the direct volume rendering, the X-ray and MIP, the strengths, it's like a radiograph. And so if you're used to looking at radiographs, that's useful. Every voxel contributes, that you can't hide some data in there and have it be completely removed. And it shows fuzzy boundaries. The weakness is we're going to see a shape in this that's due to the luminous variation that's not really a shape of the object, right? And so we're going to have issues with that. Surface-like, so the strengths, the opaque surfaces include others, and they can show fuzzy boundaries, but again, if we're viewing this thing, it's put together as an over-operator, we're viewing it as an illuminated solid object, surface object, and so we're going to get some distortions in the shape perception that way. And the lit colored surfaces are just like, if you did it by extracting isosurfaces and rendering them. It's just a faster way to render it. Physically based, it's good if you know what the materials are you're looking for. You can just extract exactly the ones that you want. Fuzzy volumes are hard to tell what's going on, right? And so you don't get good surface boundaries on that. The exotic, the strengths is there's lots of flexibility. You can tune to a particular task. The bad news is you're going to see something, And it may not be actually data relevant, it may be artifact of the particular settings you have on your transfer function. All right, I've run us past time, so I'll finish this lecture at the beginning of next class. I'm going to go through it in about 2 seconds here, but I'll go through it faster, slower next time. All right, glyphs, you can color and size changing glyphs, you can put them in space, you can use the color and the size to give two informations about what's going on. You can take these spots and move them around in space. I'll tell you the story about the drink next time. And yeah, all right, good. Sorry. I wanted to give you all this because you're going to be starting working on a design for next time, so you at least have seen them. They're in the notes online, but I'll go through it Tuesday at normal speed, and then we'll have the rest of the Tuesday lecture.